Now we are going to learn the difference between mass and weight. So last time we have learned about mass. Remember, mass is a measure of an object's inertia, which is its resistance to change in motion. So basically, the more massive on an object is, the harder it is to speed up or slow down. And the unit we use for mass is the kilogram or kg. Now let's talk about weight. Weight is a force. Specifically, it is the gravitational force acting on an object. So that means if there is no gravity, an object actually has no weight at all. And because weight is a force, its unit is Newton or N. So you might be wondering, how are mass and weight related? This is where Newton's second law comes in. Since weight is a force, we can use the formula F equals ma, where the force is the weight and the acceleration is the gravitational acceleration. So we get the formula weight equals mass times gravity, or W equals mg. Now here's an important idea. Gravity is the same near the Earth's surface, but the gravitational force, the weight, depends on the mass of the object. So two objects with different masses will have different weights, even though they experience the same gravitational acceleration. So for example, a feather and a hammer fall at the same rate in gravity, but their weights are different because their masses are different. So to summarize, mass is an intrinsic property of an object. It doesn't change no matter where you are. But weight, on the other hand, is the gravitational force on that mass and can change if the gravity changes. So keep this in mind as we move on to the next section. Now that we have gone through the concepts, let's do some exercises to practice calculating mass and weight. Suppose a woman has a mass of 50 kilogram. So what is her weight in newtons? And what is her weight in pounds? You have been given 1 lb is equal to 4.45 newton. Okay. Now we have been given the mass. Mass is 50 kilogram. First let's calculate the weight in newtons. So we can use the equation weight equals mg, W equals mg. So weight is, mass is 50 kilogram and gravity is 9.8 meters per second square. Therefore weight is 490 kilogram meters per second square, and we know that kilogram meters per second square means newton. So weight is 490 newton. Now let's find the weight in pounds. For that, we can use the unit conversion, right? We know that 1 lb is equal to 4.45 newton. It's given. So W is 490 newton. So we have to multiply it by 1 lb is equal to 4.45 newton. So we wrote it as a fraction so that the unwanted unit here, newton will cancel out and we get the unit in lb, pounds. Therefore W is 490 divided by 4.45 lb. That means it is 110 lb, right? Now here's our next practice question. A ball is hanging from a string attached to the ceiling. So what do you think the net force acting on the ball is? Is it downward, upward, or zero? Now take a moment to think about it. So the correct answer is 0. So let me explain why. The ball is hanging at rest, so it is not accelerating. And if an object is not accelerating, then the net force acting on it must be 0 according to Newton's second law of motion, right? If A is 0, then net force should be 0. Now there are two forces acting on the ball. First, there is the tension from the string pulling upward, the tension force, right? And second, there is the gravitational force pulling downward, W, which is equal to mass times gravity. So these two forces are equal in magnitude but opposite in direction. So they cancel each other out. That's why the ball stays hanging quietly. The net force is 0. Net force is 0 because this T and W are equal. Therefore, it is 0. So a good tip for understanding these problems is to draw a simple diagram showing the forces with arrows. Visualizing these forces helps make sense of why the net force is 0. So in the next section, we will learn how to draw these forces clearly and solve more complex problems using force diagrams. So before moving to next section, here's another practice question. So two masses are connected by a string and placed over a fixed frictionless pulley. If mass M2 is larger than M1, M2 is larger than M1, will the two masses accelerate? So your options are yes, no, or you can't tell from this diagram. So now take a moment to think about it. And the correct answer is yes. So why is that? So mass 2, M2 is heavier, right? So that means it will fall downward. And then mass M1, which is connected to M2 by the string, should rise. Right? So both masses are connected, so their movements are linked. And as the heavier mass falls, both masses will increase their speed over time. And importantly, they will have the same magnitude of acceleration. They will have same acceleration because the string forces them to move together. So this is a classic example of Newton's second law in action, where the net force causes acceleration in the system. So a helpful strategy is to visualize or even sketch the system, showing which way the forces acts. So this will make it much easier to understand the motion and acceleration. Now that we have practiced how forces cause motion and how objects interact over strings and pulleys, it's time to move on to a very important concept in physics, Newton's third law. Now, Newton's third law is actually a pretty simple principle, and we often call it the action-reaction principle. So what this means is that for every action there is an equal but opposite reaction. Here action means a force. So whenever you apply a force to an object, that object always applies an equal force back on you in the opposite direction. So we can state Newton's third law more formally like this. If object A exerts a force on object B, then object B exerts a force on object A, and that is equal in magnitude but opposite in direction to the force on B. So let's look at an example. Imagine you are pushing a chair. So if you apply a force F1 on the chair with your hand, the chair pushes back on your hand with the force F2, and that is equal in size but opposite in direction, right? F2 is equal in size but opposite in direction. So you can even feel this force pushing against your hand. So using this notation, Newton's third law can also be written in symbolic form. F2 equals minus F1. So the minus sign here simply tells us that the two forces are in opposite directions. So one key point to remember is that when applying this law, it's very important to correctly identify all the forces acting on an object. So in this next slides, we will learn how to do that exactly. So let's consider a book lying on a table. What forces are acting on this book? Take a moment to think about it. First, we know that the weight of the book is always acting downward, right? So this is due to gravity, the earth's pull on the book. It is always acting downward, no matter where it is. Next, there is the force due to interaction of the book with the table. So we call this normal force. So we use the symbol N. So the word normal here means perpendicular. So the normal force is always perpendicular to the surface of contact. Now let's identify the action-reaction pairs. What is the reaction force to the Earth's gravitational pull on the book? And what is the reaction force to the table's normal force? So the reaction force to the Earth's gravitational force W acting on the book is an equal but opposite force, right? According to Newton's third law, it should be equal but opposite. So it should be minus W. So it is the force that the book exerts on Earth. So the Earth pulls the book downward and the book pulls upward on the Earth. Is it really pulling the Earth? Since the Earth's mass is enormously larger than the book, this upward force is extremely small. So we don't really feel it. Next, the reaction force to the table's normal force, N, which is exerted upward on the book, is an equal force minus N. So this is the force that the book exerted downward on the table. So by identifying these action-reaction pairs, we can better understand how forces interact in everyday situations. So for every action force, there is a reaction force which is equal in magnitude and opposite in direction. And one important thing to note about action-reaction forces is that they always act on different bodies. That means if the action force is body A acting on body B, then the reaction force is body B acting on body A. So if a problem is asking about a quantity related to the book, we focus on the forces acting only on the book. So in this example, those forces are weight and the normal force W and N, which both act on the book, right? And minus N and minus W are not acting on the book, right? Minus N is acting on the table and minus W is acting on the earth. But we are considering only the forces acting on the book, which are W and N. And another important point is the table's normal force N acting upward on the book and the earth gravitational force W acting downward on the book are equal and opposite, right? This N and W are equal and opposite. But they are not action-reaction pairs. Why? Because they act on the same object, the book. Remember, true action-reaction pairs always act on different bodies. Therefore, N and W are not action-reaction pairs. So the action-reaction pairs are N and minus N, W and minus W acting on separate objects. So keep this principle in mind as we work through more examples, because identifying which forces are action-reaction pairs is essential for solving problems correctly. Now let's think about a mule pulling a cart. You might be wondering if the cart pulls back on the mule with the same force. How does the cart actually move? Let's break it down. There are two main forces acting on the cart. First, the pull of the mule forward, F1, and second, the friction force from the ground. so which acts in the opposite direction. So to understand how the cart moves, we need to consider the net force on the cart, right? That is the total force after combining all forces acting on it. So if the force applied by the mule is greater than the frictional force opposing the motion, that means if F1 is greater than F, this friction force, then the cart experiences a net force, and as a result it will accelerate forward. So the key takeaway here is this: to figure out what forces are acting on any object, we first need to identify the other objects it is interacting with. So some of these forces will be obvious, like direct contact forces. Any object that touches or interacts with your object of interest will contribute a force that you need to consider. For example, here the frictional force from the ground, because the cart is touching the ground, right? Alright, that brings us to the end of section 2 and 3, where we covered mass and weight as well as Newton's third law. So we explored the difference between mass and weight, learned how to calculate weight using the equation W equals mg, and practiced identifying action-reaction pairs in a few situations. So in the next section, we will move on to applications of Newton's laws, where we will learn how to apply these concepts to solve real physics problems. So this will include identifying forces, calculating net forces, and predicting the motion of objects.